Standing at the beach, have you ever wondered how far you can see? The ocean graduates to a flat blue line, but where does that line end? After a ship leaves port, how far must it be before you can no longer see it? The concept we're discussing is line of sight. Now, ordinarily this is a very simple premise, a straight line from eye level in the direction you're facing. In the case of the horizon, however, the limiting factor is Earth curvature. With a non-obstructed field of view, the furthest away object that can be seen is the last point before the Earth curves out of sight. An easier way to imagine this is as follows. Picture yourself standing on top of the arch of a bridge, facing along the path. As the arch curves away from you, it falls out of sight. Your vision is blocked by the arch itself. The Earth curve line of sight principle is the same, only amplified. So how do we assess this? The formula involved is called the secant tangent theorem. OC squared equals OA times OB. Put simply, the diameter of the sphere plus the height of an observer multiplied by that observer's height alone equals viewing distance squared. For a person of eye level 1.8 meters, standing at sea level on our Earth of 12,700 kilometers in diameter, their viewing distance is 4.79 kilometers.
Let's look at that secant tangent theorem. For the Earth, this is viewing distance squared equals the diameter of the Earth plus the height of the observer above sea level times the height of the observer. In this instance, when we simplify this formula, it becomes 3.57 times square root of h.
While the distance of the horizon may be a common trivia night fact, it is clearly not the same for all people and locations. As a person's height increases, their viewing distance does also. This increase is not a linear one at that. Let's look at why. With the average fully grown adult being able to see nearly 5 kilometers, you'd expect a child to see just a fraction of that. This is not the case. For a child of eye level 115 centimeters, the horizon is 3.8 kilometers away. This means, despite a viewing height just 63% of the adult, a 5-year-old can still see 80% of the distance. Now, as we said, this line is an exponential. While the graph pictured looks more or less like straight to the untrained eye, this is only because of the minimized ratio of the height of a human compared to the diameter of the Earth. When we add some more viewing heights for reference, the shape of the curve becomes more visible.
We have placed a few interesting points on the graph. The starting point for the line is the viewing distance of an average adult, 4.7 kilometers. From there, the second point is the quickest and easiest way to increase your elevation, standing on someone's shoulders, increasing viewing distance to 6.7 kilometers. From there, a few more low elevation points listed include standing on the roof of a house, the top of a 10-story building, and a few more well-known man-made icons. Australia's tallest building, the Gold Coast's Q1, will allow a viewer to see 64 kilometers away. Looking internationally, the world's tallest building, the Burj Khalifa in Dubai, is 828 meters in height and allows a person to see just over 100 kilometers away. On our graph, it is from this point onwards that we really start to see a curve form. Mount Kosciuszko, Kilimanjaro, and Everest allow a viewer to see 168, 274, and 336 kilometers respectively. This of course assumes a clear line of sight to sea level without environmental obstructions. For someone with a window seat on an A380, without clouds they will be able to see more than 400 kilometers away. That's nearly 2/3 of the viewing distance of the pilot of the highest suborbital flight in history. The SR-71 Blackbird flew to 26,000 meters, allowing a viewing distance of 575 kilometers. Beyond this, two more points of interest include the furthest a person has ever seen inside our atmosphere, while not enclosed in a plane or shuttle. Felix Baumgartner skydived from the height of 39 kilometers, allowing him to see 705 kilometers of the Earth's surface in any direction around him. In the ultimate case, a viewer must be at least 2,640 kilometers from sea level to view one full face of the Earth. When comparing the two graphs, an interesting point becomes apparent. The person height graph can almost be viewed as a tangent line near the origin of the elevation graph. What this means is that if you were to choose a point near the beginning of the higher elevation graph and magnify it to a point where the curve is almost indistinguishable from a straight line, it would look very similar to the curve of the eye level graph. With the creation of tangent lines, we are able to view instantaneous rate of change of the curve at a point. At 5 points on our elevation graph, tangent lines were generated. The gradients of these tangents were 0.67, 1.33, 38.61, and 94.2. These figures state the elevation increase required in order to gain an additional 1 kilometer in viewer distance at the chosen intervals. From this information, we have proved that the curve is an exponential. If the gradients at all 5 points were the same, the graph will be straight. At the end of the curve, for a 1 kilometer gain in viewing distance, we need approximately 140 times the elevation increase necessary for the same result at the beginning of the graph.
This graph of the derivative features a positive increasing concave up curve. It is very similar in shape to the elevation graph, as the original is a non-parabola exponential that starts and ends in the same quadrant. Now that we have considered the relationship of elevation and viewing distance, we can investigate the influence the size that the planet has. For this comparison, we have chosen bodies both smaller and larger in diameter than Earth, our Moon and Jupiter. The Moon is just a fraction of the Earth's size. With a diameter of 3,474 kilometers, it is roughly a quarter of Earth's size. Jupiter, however, is considerably larger than Earth, with a diameter 139,822 kilometers. Earth is just 8% of this size. Due to the difference in diameter, the planets curve away from a viewer at different rates. A larger planet leaves more surface area visible to an observer before falling out of sight, while the opposite occurs for one that is smaller. Let's put this in perspective of our stuntman Felix. If he were to plan to skydive from an elevation resulting in the same 705 kilometer viewing distance above Jupiter, he would only need to be 3,581 meters above the surface, less than 10% of his 39 kilometer altitude jump above Earth. If, however, he attempted the same task on the Moon, he would need to be a staggering 143 kilometers above the surface, more than 3.5 times his accomplished altitude. Fortunately though, we don't have to worry about skydiving from outer space. For a significant portion of history, these facts were integral in communication. The furthest a message could be sent, for example, depended on how high a smoke signal would travel. For most of us though, the only real time we ever wonder how far we can see is when we have the waves crashing at our feet.